start with a talk by Youness Lamzouri on large fixed-order character types.
Okay, thank you. So first of all, I would like to thank the organizers for inviting me to speak today. So I'm going to talk about large character sums, but more specifically for characters having a fixed order, like quadratic characters, cubic, and so forth. So here throughout, chi will be a primitive character or Dirichlet character mod q. So q is not a prime necessarily. And so, of course, bounding character sums has many applications in number theory. And one particular quantity which has received much interest is this quantity m of chi. So this is the maximum that the character sum can be. So up to, let's say, t chi of n. And of course, you can maximize over all t's, but because we have periodicity and the full sum up to q is 0, you can simply focus on t up to q. Okay? So what do we know about this? Well, trivially, by bounding everything by 1 here, you get a trivial bound. But of course, we can do much better than this. We can have square root constellations. And this is the classical Vinogradov inequality discovered independently by Polya and Vinogradov in 1918. So what the Polya-Vinogradov inequality tells you is that m of chi is bounded by a constant square root q log q. Okay, so you have square root constellations, and in fact, Polya-Vinogradov inequality has many applications, and I will give you a concrete one in a few minutes. But we can ask ourselves, is this optimal? And the answer is no. So by the way, this is still the best known unconditional bound from a century ago, except from special cases. But if you assume the generalized Riemann hypothesis, then you can do better. So this was proved by Montgomery and Vaughan in 1977. They proved that m chi, so maybe let me put GRH somewhere here. So assume the generalized Riemann hypothesis, then m of chi is bounded by a constant square root q log q. Okay, so you can go from log q to log q. So for people who are not expert, they might, this improvement might seem very small, but actually just improving the constant in Polya-Vinogradov will have tremendous applications, as we shall see in a minute. Okay? And so why this is important? Because, in fact, the Montgomery-Vaughan bound is optimal. And this is due to a result of Palais from 1932. And this is unconditional. There exists infinitely many quadratic characters chi mod q for which the character sum can be that large. Tilde square root q log q. So throughout the talk, whenever you see a constant with a tilde, think of it as an omega result. So there exists infinitely many characters for which you can assume this bound. Okay? And so you can ask, well, this is best possible, but what about the constant? So Granville and Soundarajan a few years ago refined the Montgomery-Vaughan bounds. What they proved is 2007. If you assume GRH, so if you assume GRH, then you can take the constant in Montgomery and Vaughan to be the following, depending on the parity of chi. So C1 is 2e to the gamma over pi, if chi is odd. So meaning that chi minus 1 is minus 1. And 2e to the gamma over pi squared 3 if chi is even. And as, or similarly to many of these problems, in fact, GRH does not give you the full truth. What you expect the truth to be are half of these constants. So they also proved an omega result, showing that there are infinitely many chi odd, chi mod q odd, for which C1 can be, or C1, let's call it C1 tilde. The omega result is e to the gamma over pi. And similarly, there are infinitely many chi even, for which you can attain e to the gamma over pi squared 3. Okay. And their conjecture is that these are best possible. Lamzouri, these constants are best possible. Okay. And in fact, recently, a result by Bober, Goldmacher, Granville, and Koukoulopoulos in 2014 studies the distribution of M chi Here, chi varies mod q. So primitive character is mod q, and q is prime. Okay. And the results show or give strong evidence for the Granville-Lamzouri conjecture that these bounds should be best possible in the Montgomery-Vaughan. Gamma is the Euler constant. Yeah. Euler-Mascherani. So I promised you an application of Vinogradov, and it is in fact a very nice discovery of Bober and Goldmacher that tells you that if you can improve even the constant C0 in Vinogradov, then you can improve the current bounds for the least quadratic non-residue. So you can beat the Burgess bounds. Okay, so this is Bober and Goldmacher. In 2014. So what they proved is the following. So first of all, okay, so maybe let me just, before stating the results, give you what do we know about the least non-quadratic residue, modulo P. Quadratic non-residue. Modulo prime. The best bound that we know is due to Burgess from the 60s. And the Burgess bound is something like NP less than P to 1 over 4 square root E plus little 1. Okay. We believe much more should be true. So we believe what's called the Vinogradov conjecture, which is that NP is bounded by P to the epsilon. Okay. And in fact, on GRH, you can do much better. So on GRH, the Vinogradov's conjecture is true, and in fact, the least quadratic non-residue is in fact even smaller than P to the epsilon. On GRH, you can show that NP is less than log P squared. Okay. So big O log P squared was due to Ankeny from the 50s, and this explicit result is due to myself, Xianan Li, and Lamzouri. So this is the current knowledge on NP. Now what Bober and Goldmacher did was the following. So first of all, they show that if you take the best known constant in the Vinogradov, which is due to Hildebrand, C0 above, so this is due to Hildebrand, you recover Burgess. So this implies the Burgess bound for NP. And if you can just make the constant there go to 0 as, so not even Montgomery and Vaughan, just take C0 and make it go to 0 as Q goes to infinity, then you recover Vinogradov. So C0 goes to 0 implies the Vinogradov conjecture. And in fact, if you throw in the best possible result that you can hope for, which is this conjecture of Granville and Soundarajan, that half of these bounds should be attained, then you get something stronger even than GRH. So Granville-Soundarajan conjecture for C1, in fact, in Montgomery and Vaughan, this implies something even stronger than GRH. So NP is less than log P to the 1.37. While GRH only gives you log P squared. And what we believe the truth should be log P to the 1 plus epsilon. That's what we believe the truth. And you can see that GRH also gives you sort of twice the expected truth. All right, so now let's talk about fixed order characters, which is the topic of this course. It's something ugly. So it has square root 3 e to the gamma and e in it. So maybe Leo can, no? You don't know, right?
Is there any sort of reverse implication? Or something about NP tells you something about Vinogradov?
Yeah, so you bound, I think so. You can bound the character sum in terms of NP, right? That's what your result is with Goldmacher. So if you know something about NP, you can know something about the character sum as well. Okay, so maybe here let me just add the definition of an order of a character, which is simply the order as a homomorphism. So order of chi is n. This is the same as chi n is 1, and n is the smallest, and such that this is true. And remember this result of Paley that gives you quadratic characters for which the character sum is large, so for which it is something like square root q log q with a constant. And we will see that this situation is very similar if the order of the character is even. So for even all the characters, which are actually the hardest one, and up to now, we do not have any improvement over Polya-Vinogradov for these. But we can say something about the omega results. So for the omega results, extending Paley's Granville and Sound in 2007, they proved that for any k in n, if you assume GRH, then there exists infinitely many characters with order 2k. Okay. For which, let me continue here. So for which the character sum gets as large as the square root q log q, so with a constant. So such that m chi is at least ck, or ck, let's say tilde, square root q log q. So, and this is for any k. But of course, the drawback is that it assumes GRH. And a few years later, a result of Goldmacher and myself removes the GRH. It was 2014. And we can prove this result unconditional. So unconditional. However, the drawback of these results is that the constant here is really small. And in fact, it goes to 0 once k goes to infinity. So here, in fact, let me say that the method here relies on some Fourier analytic techniques developed by Palais. So more or less hitting this character sum with a fair kernel. And so we'll see some ideas when I talk about the proofs later on. But in any case, the constant here in both these results goes to 0 as k goes to infinity. Okay. And so you might wonder whether character sums, if the order is really large, will be much smaller than those, let's say, for quadratic characters. But actually, it's not. So you can get the best possible constant in the omega result. And this is a result of myself from last year. So you can take ck tilde, be exactly what you expect, which is e to the gamma over pi for old ones, and e to the gamma over pi squared 3 for even. So meaning that there exists an infinite family of characters chi of order 2k, which are odd, for which this is attained, and also similarly for the even case. And not, yeah? No, unconditional. So removed. So already we removed the unconditional part. So this is unconditional. And also, no, for both. No, we got it for both. Yeah.
Oh, I see with the other aspect.
Yeah. So not only that, but in fact, we can. So also in both these results, the order is fixed. Otherwise, the constant goes to 0 as k goes to infinity. But in fact, in here, you can even take the order uniformly up to log q to a certain power and still get the best possible result. And let me just say a few words on this. So while in here we use some ideas of Palais, here we use more. So this is more like Fourier techniques. This is more analytic ones relating the character sum to values of L1 chi. We know a great deal about values of Dirichlet functions at 1, and this allows us to get the best possible result. Okay, so now let's see what we know about odd order characters. And actually, we know more and less, as you will see. So we know more that in the sense that both the Vinogradov and the Montgomery-Vaughan bounds can be improved in this case. And this is a breakthrough of Granville and Lamzouri. This is the main result in the paper. So here let me take G to be greater than or equal to 3 odd throughout the talk, and G will be fixed. So what Granville and Lamzouri proved is that, so to state the result simultaneously for Vinogradov, which is the unconditional case, and Montgomery and Vaughan, which is the conditional one, let me add this variable here, capital Q, which will be throughout the talk, let Q unconditionally, and log Q on GRH. And you can express all these results in terms of this capital Q. So square root Q log Q, this corresponds to both Vinogradov and Montgomery and Vaughan on GRH. And what they proved is that you can have a power saving in the log. So now what is this delta G? The delta G is this constant here, 1 minus G over pi sine pi of G. And this is positive in this case. So you have a power saving. So Goldmacher in his thesis, so Granville-Lamzouri also conjectured that you should be able to get the full constant delta G, not delta G over 2, and that the conditional part with delta G will be or should be best possible. And this was proved by Goldmacher in his thesis in 2012, appeared in 2012. So you can improve this to delta G, so log Q 1 minus delta G, and the conditional part here is best possible on GRH. So GRH implies, again, there are infinitely many chi of order G for which this is best possible. Only the unconditional parts, and so we have log Q in this case, 1 minus delta G, let's say minus epsilon. Okay. So again, a few years after this, or in fact, it appeared at the same time, but it's roughly a few years after it, Goldmacher and I were able to remove GRH from the B result. So B is unconditional. And so we know a great deal about all the other characters except this. Oh, here, sorry. Should have a little 1, 2. So we know optimality with the power here except this nasty epsilon. Can ask ourselves what this should be. Or should it be there, or should it not? Maybe we can just have a very clean result, and that this is optimal. So this motivated my recent work with Montreal. We posted the paper on the archive last month. So this was 2017, in which we can, in fact, refine this epsilon and conditionally get something more or less optimal up to a fourth power of log q, up to a power of log 4q. So this result here will prove to you that this is a real analytic number theory talk, because it will have many logs and triple logs, quadruple logs. So we go more precise than this. So here, let me just write down log sub j to be the jth iterate of the log. So log 2 will be log 3 will be triple log, and so on. And here is the results. So the unconditional and conditional case, unlike here, will differ slightly due to the possible existence of Siegel zeros, and we can't go around them. So first theorem will be upper bounds. So here, unconditionally, we can improve Polya Vinogradov further. We have m of chi is less than square root q. Again, I mean the same assumptions. So chi order g, or order chi is g, and odd. So you get log q, 1 minus delta g, double log, minus a quarter, and a plus epsilon. Okay. And the problem here is that, so this is unconditional. The problem is that this nasty epsilon here, we can't really go around it, and I will tell you why. So unless you know that there are no Siegel zeros. So this is coming from Siegel zeros, or let's say exceptional discriminants. And if there are no Siegel zeros, then you can do better than this. So no Siegel zeros. You can replace this log 2q to the power epsilon by a power of triple log q, which is much smaller. Okay. And again, the conditional result will be everything gets scaled from Q to log Q. So whenever you see a double log, should be a triple log, and so on. And on GRH, you can do the following. So less than square root Q. You improve one before, so you get 1 minus delta G, log triple, minus a quarter, and fourth power of log big 1. Okay. And the surprising fact comes after this that says that this ugly expression here is really optimal. This is best possible up to the power of log 4. So this is theorem 2. Maybe let me write it here. So maybe let me erase this and rewrite it here because I want these results to stay a little bit longer. Chi square root Q, log 2Q, 1 minus delta G, log 3, triple log minus a quarter, and quadruple logs. And then our theorem 2 says that this is best possible and conditional. So there are infinitely many chi of order G such that this is attained. And so in fact, as you will see in the proof, the only difference between the GRH case and the unconditional one is the scaling, so Q goes to log Q. And so you might think of the above improvement of Vinogradov as being the limit of the Granville-Soundarajah approach. So if you want to beat this, you need more ideas. OK, so in the remaining part of the talk, I would like to discuss the ideas in the proofs. For this one, we don't have any information about the order other than, well, yeah, more or less it's, OK, so our construction involves product, let's say, of 3 primes, more or less. OK, so I will tell you a little bit about it, hopefully, just how to, if I have time, how to. But in fact, it doesn't. All right, so the starting point is Polya's proof of the Polya-Vinogradov, yes? Minus a constant plus a constant. Yeah. We can do it explicitly, but it's just we were a little bit lazy. But no, I don't think a million is. Maybe 100, something like this should be fine. Yeah. So, this I'm not completely sure, but I think it does. Yeah. But at least the constant here depends on G, that's for sure. Okay. So ideas in the proof. So let's start with the starting point where everything started, which is Polya's idea in proving the Polya-Vinogradov. So Polya's idea is to have a Fourier expansion for the characters. So if you look at this function here, let me start here, and up to alpha q, and think of alpha as being the variable. So alpha here is positive and real. Then this is, in fact, a function that is both periodic with period 1 and of bounded variation. And so it has a Fourier expansion, which you can write in truncated form as follows. So Pa of chi will be the Gauss sum, which I will define. And here you have the sum n. So I'm truncating the Fourier expansion. So chi bar n over n, 1 minus e minus n alpha. And then there is a small error, log q, a very small one. Now, as we saw before, many talks, and particularly in Philippe's talk, e to the e to the minus alpha, or e to the x, will be simply exponential of 2 pi x. Okay. And this here is the Gauss sum defined by n mod q chi n e to the n over q. Okay. And we know that if chi is primitive, then the Gauss sum has absolute value square root q. Okay? And so in fact, just from here, a very easy exercise is to take just absolute values everywhere, and it gives you Vinogradov for free. So square root here, square root q, constant, 1 over n, constant, and you're summing up to q. This is log, and you get square root q log q. Okay, so that's Pauli's proof. And so it's clear that if you want to understand the character, so understanding m of chi, which is in fact the maximum over all alphas of such character sum, so you can take the maximum here, you need to understand the following exponential sum, chi n over n e to the alpha and to the value of n up to k. So whenever I write this, it means that it starts at 1. All right, so I don't need to write greater than or equal to 1. So we need to understand this, and it's clear from Pauli's proof that any non-trivial information about this quantity there will give you non-trivial information about the character sum. Okay? So in particular, to prove the Montgomery and Vaughan bounds, Granville and Sandro-Agen used GRH to extract a non-trivial information about this. So what GRH gives you, as in many other problems, it gives you that this sum here can be truncated, and only the integers that have very small prime factors will matter. So we can approximate the sum by sum over smooth numbers or friable numbers. And this is true for all alpha. So up to q. So p divides n implies p is really small, something like log of power, or power of log of the same sum. I can add here. If I take this A large, then I can add just a little of 1. It's fine. And so this is why I tell you everything gets scaled from q to log q, because once you have this information, you plug it in the Fourier expansion, you bound this, the bound for here will be simply, or roughly, so bound everything trivially, taking absolute values, the bound will be something like, so it will be the sum n up to q1 over n of this, which is roughly exponential of the sum over primes, where the primes are small, and this is log q. So this gives you Montgomery. Okay. And all in the proof, in fact, of all results, the GRH conditional ones exactly use only this step. So whatever unconditional proof you have, you hit it with this step here, and it rescales everything from q to log q. All right, so let's see what we can get. What type of information can we extract from this exponential sum if chi has order g? So when studying exponential sums, I mean, the first hint that you have, which suggested by the circle method, is to approximate by a rational. That's what the circle method tells you. You have an exponential sum, you want to study it, then approximate by rationals. So circle method tells you you should take alpha very close to rational. Okay. So before elaborating more on this heuristic, which in fact can be turned out into a rigorous proof, let me just take alpha to be a rational and see what the character sum will be, or the exponential sum will be here. So if you take alpha to be exactly b over m, then this guy here will be what? Well, e and b over m. So the advantage of having a rational is that you can express this additive character in terms of multiplicative characters. That's the idea. More or less, think of it as being Fourier inversion. So you can write this as 1 over phi m, the sum over all characters psi modulo m, the Fourier transform of psi at b, which is something like psi bar b tau of psi, which we can understand very well. And then the inner sum here is something that we can understand more than exponential sums, which is a sum over completely multiplicative functions. So chi psi bar n over n. Okay. And of course, let me point out that because we have absolute value here, less than q, the only psi's that matters are the ones that have opposite parity to chi. If chi and psi have the same parity, then by flipping this sum, considering the positive and negative, this sum completely vanishes. Okay? And so from now on, let me just talk about those psi which have opposite parity to chi. Okay? Otherwise, this sum is 0. All right, so let's go back to the circle method. Now let's talk about the upper bounds for m chi. So in the circle method, you expect that if alpha cannot be approximated by a rational with a small denominator, then this guy here will oscillate a lot. And if it oscillates a lot, you expect this sum, or the sum there, to be small. So this is the case that we call the minor arcs. And it was indeed proved by Montgomery and Vaughan that in this case, the exponential sum above is small. So if alpha is in a minor arc, meaning, okay, maybe here let me write this as star, then star is small. Okay. And so you only need to focus on the most difficult case of major arcs. So in this case, you can approximate alpha by a rational with a small denominator. So alpha in a major arc simply means that alpha is very close to b over m, with m a rational with a small denominator. So let's think of m as being less than log q to the power a. I'm cheating here because to consider the GRH case, you need log capital Q here, so log in the GRH case, but it's fine. So everything gets scaled back to log Q. So this is a major arc case, and in this case we saw that if we can approximate the character sum, or the exponential sum in terms of b over m, then we have this nice sort of identity here that brings everything to completely multiplicative functions. So, so in this case, Granville and Soundrajan proved that star is in fact very close to a sum where you replace alpha by this b over m. But the problem here is that the length of the sum gets altered. So instead of n being up to q, n now is up to capital N, where capital N is some something that depends on all these parameters. So here, n of alpha, b, m, and q. Okay. And now the advantage here is that is that m is small, so the conductor of psi is small, and you can bring everything in terms of. So this can be brought in terms of the following sums. So n up to n now, chi psi bar n over n. Okay. And what are the conditions on chi and psi? Well, you need psi to be of opposite parity. We started with chi having order g, and you need, you are in a major R case where m is small. So m is the conductor of psi. So psi mod m small. All right, but now the advantage is that we transformed everything in terms of multiplicative functions, and we can use the technology that we have for completely multiplicative functions. This is exactly what Granville and Lamzouri did. So if you look at this sum here, the only way for this sum to be large is if chi and psi are very close to each other, so that chi psi bar is close to 1, right? And for multiplicative functions, completely multiplicative functions, it's enough to consider the behavior on primes. So when chi p is close to psi p on primes. And so this is where the pretentious theory of multiplicative functions more or less started. You can, in fact, and this is Granville and Lamzouri ideas, or ingredients are the following. So first of all, you relate this to roughly what's called the distance between chi and psi, which measures how close chi p is from psi p over prime. So they use the following bound. I'm going to define exactly what this distance, which is actually a pseudometric, so it's not really a distance. So exponential minus d square chi psi n. Oh, yeah. Let's bring everything in terms of x. Here. Okay. Over 2, that's essential. Okay. And what is this distance? This is the following. So if you remember from Max's talk, we saw this more or less 1 minus fp over p. Here we are in complex value, so it's real. And instead of, so you measure the distance from chi p to psi b, so chi psi bar at p over p. And to make this a distance, you need to take square roots for it to satisfy the triangle inequality. So let's call this step here step 1. Okay, so now that you brought everything in terms of the distance, you can simply understand what this distance be, and then hopefully you will win. So the first or the second step tells you that you actually do not need to consider all psi mod n, but only one psi matters. And let's call this repulsion. So what happens is, because these psi's have all a small conductor, so their order is small, meaning that they take values on the roots of unity, but roots of unity that are spaced in the unit circle. And so two psi's cannot be really that close to each other. And so if chi is close to 1, then it has to be further from the others. That's exactly what this phenomenon will tell you. So only one psi matters. And when I say psi, it's primitive. Matters. And now what makes you win is the fact that, recall here, we only need to study this for chi and psi, which have opposite parity, and psi has a small conductor. And if you think about it, if chi has order g, then chi is then chi is necessarily even. And so psi from here is necessarily odd. which means that psi has an even order. So you're trying to approximate an odd order character with an even order character where the conductor is really small. And you can do that. So what they proved is that in the third step, the distance between chi psi and x is delta g plus little o log x. Okay? And so putting everything together will give you a saving of delta g over 2 here. Okay? But the problem is how to get rid of this 2. And this was the essence in Goldmacher's work. How to get rid of this 2, how to improve this and has an exponent that is exactly 1, and then go from there. So instead of using this inequality that relates mean values of completely multiplicative functions to the distance, Goldmacher used a version of Haller's theorem. So Haller's theorem is really the best ingredient to study mean values of complex valued functions. And here we are talking about logarithmic summatory functions. So he used a sort of logarithmic Hallas, which was proved by Montgomery and Vaughan, and with refinements of Tenenbaum. So Montgomery, Vaughan, Tenenbaum. And what this tells you is that if you take f to be any completely multiplicative function with values in the unit disk, then you can bound the summatory or logarithmic summatory function of it by something close to the distance, but actually something that measures not only the distance from f to 1, which is the analog of this case here, chi psi bar to 1, but actually f to any function of the form n to the it. And you have a 1 over t here. Oh, sorry. I'm going to define this. So mxt. So let me define this one. xt, this is simply the minimum of the distance from f to an it up to x, where you're taking all these twists to be bounded by capital T. And the bound here is valid only for t greater than 1. So Haller's theorem, the normal Haller's, is more or less similar to this one, but for mean values of multiplicative functions, gives you the sum fn 1 over x here. You remove this, and then it's roughly this one here, exponential minus m. You need to multiply by m. But what Haller's tells you is that unless you are very close to an it, your mean value is small. Okay. So we will elaborate on this a little bit more in a few minutes. But now so this improves this exponent here from 1/2 to 1, which is great. But in fact, so this, let's say, improves step 1. But the problem now is that you need to understand the problem in terms of something more complicated than this one, which is not only the distance between chi and psi, but the distance between chi psi bar and it. Okay? And so this is what Goldmacher did, and he showed that both. So step 2 is not difficult to do. It was done in work of Balog, Granville, and Sound. So in step 3, you need to show that chi psi bar is in fact away from NIT and away with the same write it here. So m chi psi bar x t is at least delta g plus little to x. If t is between, let's say, 1 and log x squared. And then plug in everything together, Goldmacher got the improvement. Okay. So how do we with my work with Majorel, how did we improve this? Well, first of all, the step that needs to be improved here is really this step here. So the little one is what gives you the epsilon in the bound for m of chi. And so you need to find more precise estimate for this distance here. So this is what we do. And actually, we discover a surprising phenomenon, which is that the distance from here depends on the size of the twist. So it depends on NIT here. So it's clear from the main term that it does not, but the little O1 here changes if you take small versus large twists. So what we proved is that if you take t bounded by something small, really small, like log x to minus theta, let's say, then you can recover an additional factor which depends on the order of psi. So psi, so some constant here that depends on all these parameters over k log 2. And there are a bunch of error terms, but unfortunately, there is an error term which depends on log of L1 chi, where chi ranges over all characters with the same modulus as psi. So if psi mod m, and m is exceptional, meaning that it has a quadratic character for which L1 chi can be super small, then you have this extra term that comes from psi of zeros. And then we have something small. And if the twist is large, like in Goldmacher's, for example, the twist is 1, then this is going to be, or you're going to lose, in fact, the extra additional term. So we proved this second result on GRH, but we don't actually need, we don't actually need it in the proof, just to illustrate that we need to take small twists. So m type c bar xt will be smaller than delta g log 2x plus this really tiny factor here, log m. Remember that m is really small. And so the extra term, or this extra factor here, disappears. And let me mention if t is greater than 1. And so this brings us all back to step 1, which is Hallas' theorem. So in the normal Hallas' theorem, this is really what measures the way that the mean value is large or small. Okay? So in the usual Hallas, for mean values of multiplicative functions, if you think of NIT, for example, then NIT has a large mean value. So 1 over x sum NIT is large. So this is x to the IT over 1 plus IT. No matter what t is, it's always large. Okay? However, if you look at the logarithmic mean of NIT, then something else happens. NIT over n, this is roughly the minimum between 1 over t and x, and log x. And so this is going to be really small unless t itself is really tiny. Okay, so small unless t is small. But this case here of the small t is not detected by the Montgomery-von Tenenbaum version of Hallas' theorem for logarithmic mean, and so we needed to prove something different. And so we improved the logarithmic Hallas in this case. So theorem 3. Again, with the same assumption, but t here now can be anything between 0 and 1, where this, in fact, this is what detects where these guys are large. And you can show that this is, again, is going to be bounded by log x exponential minus mfxt. But we have also an improved 1 over t here. And as a corollary, this characterizes the multiplicative functions for which the logarithmic summatory is large, in the sense that so as a corollary, so in our work on character sums, we are interested about those for which the summatory function is at least log x to the theta, let's say. And if you look at here, this tells you that t has to be less than log x to the minus theta. And what the theorem tells you is that this is exactly the case. So this implies that f is close to 9t for some t really smaller than log x to minus theta. Okay. So with these in hand, we can, in fact, improve the upper bounds. Now, in the last 5 minutes, let me talk briefly about the lower bounds, or the omega results. We need 5 minutes for these. Proof of theorem 2. And we'll draw some differences between, in fact, the work of Goldmacher and myself and the new work. So in Goldmacher and myself, to prove that the character sums can get large, what we do is we exploit this feature that we had maximum over all alphas of this one here, roughly. So we can maximize over all alphas. So I'm cheating here, but just to give you the ideas. But in fact, using Fourier analysis techniques and exploiting this maximum here, hitting, in fact, this sum with a Fourier kernel and maximizing again, you can shorten the sum as long as you want. So you can have any short sum you want. And more or less, this is one of the key ideas in the work of Bober and Goldmacher. You can shorten these sums, and so once you shorten them to detect the least quadratic non-residue, and you make the sum large depending on where the least quadratic non-residue is. So this here goes to, by Palais, roughly Fourier analysis. This goes to something like a short sum where we can control the character sum. Alpha and up to log q. And the advantage of log q is that we can control the values of the primes of any character we want. Again, choosing alpha irrational. This brings us back to multiplicative functions. But now the sum is really small or really short. And so to bring everything in terms of primes, we need to bring everything in terms of the distance, right, between chi and psi and log q. And this one here we can minimize. We can control very well. The problem with this approach is that although unconditional and everything works fine, the sum is too short to give you exactly what you need. So you lose some primes in here, and so there is a loss of a factor of triple log q. Now, this was fine if you want to have an omega result of size log q to the 1 minus delta g minus epsilon, because the triple log get lost into the log q to the epsilon. But if you want to do something more precise, then you need to change this approach. Okay? So with Mondrian, what we do is very different. So we start by taking a choice of alpha to be exactly irrational that you want. And this brings this long exponential sum to a long multiplicative sum, right? Okay, exactly by the same technique. Just choose alpha to be this. The advantage of this one if you recognize, so if C has very small conductor, this is roughly L1 chi psi bar plus something. Okay, plus some error. And now L1 chi psi bar, we have a lot of techniques to study it, and we want to make it related to this distance here. And the way we do it is using analytic techniques related to zero density estimates for Dirichlet functions to show that you can actually approximate this by a short Euler product for most chi. So most, that's the chi. And now the Euler product is related exactly to the distance. That's really the distance. Taking logs and everything, this is roughly log, double log q, exponential of minus the distance squared. Okay. So between chi and psi bar. So we don't lose here, except we have this only for most chi. And the set of exceptional characters, by zero density, you can show it to be less than q to the epsilon. But now it makes another of the steps in my working with Goldmacher harder, because we need now to minimize this distance not only for one character, but for many characters to exceed the exceptional ones for which this approximation here does not hold. And we succeed to do this. So minimize the distance for many chi. So for many chi, I mean something like square root q, or you're ordering them up to, let's say, conductors up to q, and you can show that there are at least square root q or q to some power for which this is minimum, and then this exceeds the exceptional ones. Okay. So that's all I want to talk about. Thank you very much for your attention.
Well, thank you very much. So does anyone have any questions or comments? Yeah.
Does results have any significant difference if you take smooth sum instead of star product?
If you take, sorry, smooth sums?
Product instead of star product.
Well, if you want to take, so you take smooth ones, but you need to assume GRH, that you can approximate everything in terms of smooth ones. That's the GRH part of our results. The smooth cutoff. This I really don't know if it will change the result. I know that for Vinogradov it does, the normal one. It brings it to square root q. I think it was a result of Karl Pomer's. Yeah, I think it will disappear. Yeah.
Yeah. So you sort of flashed this fact that epsilon log n and said that this is where the C0
Right.
appears.
Yeah.
So is there a way to see heuristically?
Yeah. So okay. So let's not look at this m, just the distance itself, because it's easier. So the distance here, the most difficult part in here is really this part here, right? Okay. Yeah. And now what we do is you treat chi to be an arbitrary function on the set of G root of unity. Okay, so this is, let's say, at least the sum over, if you call them mu g, z in mu g, and you can so read part z p, more or less. And then you want to fix your value of c bar p. This will be supported on the set of roots of unity modulo the order. So this will take something like e to the L over k, where L travels mod k. Okay? And so once you do this, then this brings the whole picture to the sum of 1 over p and p in arithmetic progressions, mod n. Right? Now we do have precise forms of Merton's estimate for this. where we have the log that gives you the main term. And then there is a bizarre constant. And then something small, 1 over x, something like this. Now the problem is that this constant is expressed again in terms of L1 chi, where chi ranges over characters modulo m. So this goes back to log, let's say L1 chi n. Let's say. Okay? And so again, I mean, you can use techniques to cut this, and then some. So we don't want everything here. We want a certain average where we multiply this by, let's say, some complex numbers. So we can just take sums, absolute values. So here you can control all the factors except when you have an exceptional character. And this is what we don't really know. And this will give you, so the average for this will be log m that we saw, but even one of them will give you epsilon log m. And we can't say, so then the only way to get around this is to say, well, the character that chi pretends to be has to be coming from a modulus which is not exceptional. But we don't know how to go around this.
So does the result tell about, so for example, if you have mixed Q, do we have effective way to how to find the interval and character for having maximal character sum?
So you fix Q.
So yeah, fix Q, and how can you find character and interval achieve the maximum?
So how can you find the character for which the character sum is large? That's your question. I don't know. Like, what's the characterization for characters which have character sums are large? Well, except that you can say that it pretends to be a character of small conductor and opposite parity. But
I guess, like, I mean, your work might have some uses in like algorithm number theory.
uh-huh.
So, for example, actually finding the list, the quadratic, non-quadratic residue.
No, the problem is that everything here applies to odd order. So even order is the hardest. So we can't. So least quadratic non-residue, we can't say anything about it.